Well, thank you very much for inviting me. I've been asked to do two things. I've been asked to give a really broad overview of systems thinking and also to go into depth. And it's very hard to do both of those, so I've split the two. So it'll be the overview in the morning and the depth in the afternoon, and the depth will be my own practice. For the overview, that's also hard because that's like saying give an overview of biology or give an overview of physics. Systems has been a transdisciplinary research community that's been around now for about 100 years, and so I can't possibly present 100 years worth of research in one presentation. So I'm going to narrow it down, and I'll explain a little bit how I'll narrow that down in a minute. This is what I'll cover. I'll just give you a very, very basic introduction to what is a system. And I'll talk about the origins of system science really in two different transdisciplinary movements. There's one that came out of immediately pre-Soviet Russia and one in the United States. And every time I do this presentation, if I don't mention the relationship between systems, cybernetics and complexity, somebody always asks me, how does this connect to complexity science or something? So I'll cover that too. And then I'm going to present what I call three waves of development, or paradigms, if you like, of systems that have evolved from the 1950s to the present day. And I use the word waves as a metaphor because a wave will crash on the beach and it will throw various debris on the beach, and you can think of that debris as methodologies and methods. And then when the next wave comes along, it not only deposits new material on the beach, it also rearranges all the old material, which is what happens in a paradigm break, that often the same ideas are there, but they're rethought. And I'll explain how some of that rethinking has happened. So I'll give you some representative methodologies from each of those waves. I'll give you some of the best known practical examples, so I'll give you some of the most famous cases. I'll also give you a couple from my own practice here and there. And I'll also give you the critiques of each wave. I think that's really quite important because, and as you get into your discussions, what I'm going to do is break for a discussion point each time we get to the end of a methodology. And then after you've had your discussion about how that might relate to climate change strategy here, we can go back into looking at the critiques of that. So you think, this is how we'll positively use it, but we've got to take account of this. And I'll probably won't get to where to next is a fourth wave on the horizon, purely because of time constraints. If we have time at the end, I'll do that, but more often than not, I won't get there. So some caveats to the presentation. The areas we're talking about are truly transdisciplinary, and what I mean by transdisciplinary is that they pay no respect at all to disciplinary boundaries. They transcend those disciplinary boundaries. So you can see systems applications in a huge variety of fields, right from family therapy through to management. But I'm going to be focusing on systems approaches that have been used for policy and systems approaches that have been used for management, because I think those two are the most useful probably for where your focus is at. And even so, we're talking about hundreds of methodologies, and I'll be able to present 5 or 6 as exemplars. So they're just examples of what the paradigms offer. And if you want to follow up on different things, I can recommend reading if you're interested. It's important to be aware that everything I'm going to talk about here is about intervention. It's not conventional research where you're observing something or experimenting or interviewing people and then you produce a report and hand it over to decision makers. This is all about actually intervening to solve the problems. So you're actually getting stakeholders together and working with them, and they're doing their own solving of the issues. So a basic definition of a system, I put one up there as a first bullet point. So you have a set of parts organized in relationship with one another, and they give rise to emergent properties. And what I mean by emergent properties is things that you can't predict from any of those one parts in isolation. So I can think of a body as a system. So your body is not just a random heap of organs. If it was a random heap of organs on the floor, you wouldn't be alive. Your life is an emergent property of the fact that all your organs are organised in a particular way that keep you going. And note that also a system is not mystical. It's parts plus relationships equal system. There was a lot of criticism when systems scientists first proposed the idea of system formally in the United States, where people saying, well, how can you have something emergent that can't be predicted from the parts? But the assumption there is that people were thinking in some kind of mystical way, that there's some kind of soul or energy force that's there, but it's not like that. It's simply about the relationships between the parts give rise to something more that you can't predict from any of the parts in isolation. Now that's a very basic definition of a system, and as soon as you bring observers into the picture, then things get a lot more complicated. So, or rather, I wouldn't say, I don't like the word observer so much, I prefer to say participant, because people are active and actively engaged with systems. They're parts of the systems that they observe. And if you can think of the brain as a complex system, for a neurosurgeon, if they take a scalpel to a brain, they have to be very, very careful. They're going to be minutely careful where they cut. If you're a butcher taking a knife to a brain, just hack straight through it. The system looks different depending what perspective you look at it from. So it can be highly complex from one perspective, or it could be very simple from another perspective. And when you start to look at conceptual systems, non-physical systems, things get more complex still. So as we go through the paradigm shifts, you'll see how these kinds of ideas begin to have influence, because the assumption very early on was that you can have objective modelling of systems, and gradually that whole idea began to collapse, and new assumptions came in. So I'll start with what are really quite controversial origins of system science, and I've put 3 bullet points up there. The first one, I think, has a really good claim to be the first modern systems theory. So Bogdanov was a friend of Lenin's, and he wrote a book sometime between 1910 and 1913, nobody's quite sure when, called The Techtology. If you look at that book, you'll see it pretty much has all the hallmarks of systems theory as we think of it today. And except Bogdanov was really quite applied to the problem of how do you create a socialist society. And he basically said that organizational systems mirror natural systems, and if you don't actually mirror nature in your design of organizations, you're going to have a system that will fail. And he was talking about this with Lenin, saying really you've got to build a socialist system as a natural system, and Lenin really wasn't interested in that and basically dismissed it. And then when Stalin came to power, he had him exiled. So that was buried. Bogdanov's work was buried, and it was buried right through the Soviet era, and was rediscovered really when the Berlin Wall came down and Gorbachev was in power. There was also von Bertalanffy in the 1930s to the 1960s. And what's really interesting is that you can actually trace a bit of a link between these things. So Bogdanov supervised somebody in Germany, and that guy in Germany became von Bertalanffy's PhD supervisor. So you can see the links between the ideas. Yeah.
Does technology have a definition? Is that like a system, or does it mean anything?
I can't tell you, to be honest. It's a Russian word. Yeah. No, I've never actually asked anybody actually how you actually define technology, apart from it being clearly a systems theory, because the idea is that you look for the general properties of systems, and you can find the same general properties in ecosystems and families as you can, for example, in organizations. And it's the same principle that general system theory came up with later. But yeah, so you can trace von Bertalanffy back to Bogdanov, and what I wouldn't say is that he plagiarized it. There would be no evidence of that whatsoever. What you can say, though, is that the similarities are really quite striking. And the other thing that people now forget is that there was somebody called Angyle around in the States also in the 1930s. And if you had been around in the 1950s, you wouldn't be saying von Bertalanffy was the major figure in systems. You'd be saying Angyle was. He was the real founding father in the States. And even if it was the case that these people knew of what went on in Soviet Russia, they were not going to say that in 1950s America. The theory would have been stillborn almost certainly. So that's the kind of origins. And very quickly, in the 1950s, people began to look at the potential practical application of these kinds of systems ideas. Now, what a lot of people don't realize, unless you go back to look at the history, is how close various research communities were back in the 1940s. So the system science community, the complexity science community, and cybernetics community were all active back then. They had quite a lot of overlap. There were people working across those boundaries. Anybody who tells you that complexity science is something new, that is only developed in the 80s or 90s, it's not true. You can trace it back to people like Warren Weaver, who first proposed a complexity theory and called it that back in the 1940s. So that's the connection. They were very tightly woven together, really, in the early days, and they've drifted apart a little bit, so that there's a bit of competition between the research communities now. But nevertheless, they're still very interrelated ideas. So I'm going to start with the first wave of systems thinking. So this is when people first began to think about how can this idea of system be applied in policies and management. And I'm going to start with the methodology of system dynamics. Do people know the Club of Rome and Meadows' work? Lots of nods? Yeah, that was based on a system dynamics model, which was basically looking at how all sorts of global problems interacted to form a kind of global problematique, a massive wicked problem of global scale. The system dynamics has been used to address a lot of large-scale wicked problems and also business problems and public sector problems, social policy problems. The basic idea of it is that you can do a computer model which actually looks at the interconnections between things, and you can quantify the feedback processes. And what people have shown through experiments is that it only takes 3 interacting variables to go beyond the predictive capabilities of the human mind. So if I had a little model, I could demonstrate it. You'd be able to see how feedback loops work, and if you were to try to predict what the value of one of the 3 items would be in 5 minutes' time, you wouldn't be able to do it. So it's based on that idea that you need a computer to be able to really model these kinds of effects. You don't always have to use a computer, and I'm going to show you a bowl of spaghetti here. This bowl of spaghetti comes from one of my projects in New Zealand. You don't need to know the detail, just look at the form. So what you have here is feedback loops. So you've got one here, for example. Let's find one. You've got one here. This is about the Campylobacter, which is a food poisoning bacterium, how it gets transmitted from animals to humans. And in this particular bit, you've got the human sewage system. So you've got number of infected people going to volume of human sewage containing the bacteria. That goes to the degree of groundwater contamination, degree of drinking water contamination, and then back to number of infected people. So you can model these kinds of loops. And through quantifying the whole system, you can see very surprising effects very often that you wouldn't be able to predict through other means. Now, what I find in my own personal practice is that very often you don't need the computer modelling, that it gives a lot of insights just actually working with stakeholders to do the qualitative modelling like this. So this particular example was done in a situation where we had a national news media issue where one of our scientists in the institute where I used to work in a government research institute in New Zealand. One of our scientists had produced some research that showed that dairy cattle were basically pooing in the rivers and that human beings were getting sick from this, and that New Zealand had the highest rate of food poisoning from Campylobacter in the Western world and in the developed countries. And this had become front page headlines, and the farmers were screaming and saying it's not true. The scientists were defending themselves. You had other people saying it was human sewage, and other people saying it was wild ducks, and it was just a horrible situation where people wouldn't even come in the same room and talk with each other. So I was basically asked with the team of people I was working with to help people at least start to discuss this. We're not going to be able to solve it in one day, but to do a day workshop which will actually get people together and have a reasonable discussion. So what we did is we worked with people separately first of all. So they each did their own little models. So the people who thought it was human sewage did this bit, people who thought it was cows did this bit, and there's various other things. And then we brought them together and we asked them not to justify their view against other people's view, but to look for causal connections between things in other people's models and things in your own model. And that's why you've got all these long loops around here, because people began to connect these things up. And halfway through the day, there was this dawning realization that actually you're dealing with a whole system, and there were reservoirs of Campylobacter throughout the whole system. And it's just not meaningful to say that it's only in one place and not in another place. All of these are potentially causal factors. And so by the end of the day, people were talking reasonably again. Not that there were not still tensions. Of course there were still tensions, but at least people could talk about it. So the Limits to Growth project, I think, is the most famous example of system dynamics. This is Donella Meadows and her team. They first were commissioned by the Club of Rome in 1972 to build a model of the whole Earth dynamics, basically, and to offer some insights of where the world is going to go to. Now, there have been a lot of criticisms of this because they didn't anticipate things like finding oil, they didn't anticipate fracking, and all various things that were not in the initial model. As far as I'm concerned, that's not so important. The detail is something that can be revised through new models, and they've done that every few years. There's always a new edition of the book with new modelling. The success of that project was simply establishing the idea that there were finite limits to growth, that if we're on a finite planet, economic growth can't be infinite. And that idea was seeded, I think, and finally accepted by policymakers through this kind of project. And although we've now still got a lot of struggles to deal with issues of climate change, the majority of people would at least accept that basic notion. So what I'm going to do is ask you to get into your groups and think about system dynamics as an approach. Think about the fact that it can be used both quantitatively, if you've got the time to actually develop a model. If you've got a fast-moving problem like that food poisoning one, where there was a crisis that had to be dealt with, you can't do the quantification, you can just do the qualitative work. Think about those different uses and how they might be relevant to your work on climate change in Gothenburg. And if I can, I'll give you 10 minutes and then we'll come back together. Okay, so what happens if you're doing something like system dynamics and the thing that you're modelling changes before you've finished your model? I mean, this is one of the problems of something that needs intensive mathematical modelling. What you're modelling needs to be slow enough in its development for that modelling to be meaningful and for you to be able to actually explore different possibilities for change. What if you're dealing with such a turbulent environment that the situation is changing from day to day or from week to week? And in those kinds of situations, it's very difficult for something like system dynamics to get any kind of purchase. So climate change is slow enough to model, but what about fast-moving business and organisational problems? And what happens if the organisations to deliver on it are not adequate or they don't currently exist? And in some ways, I actually think that is an issue people are struggling with climate change. Do we really have the international organisations in place that will actually be able to deliver on climate change strategies? And I'm going to present to you something called the viable system model, which comes from a researcher by the name of Stafford Beer, and he started developing this in the 1950s. It comes about through bringing together cybernetic and systems ideas. And it's a model of an organisation. And one of the basic assumptions of this model is that you say the people in the organisation can work out for themselves what needs to be done, but what you can do is structure the organisation in such a way that it enables them to be flexible and responsive to the issues in their environment, and they can deal with more turbulent organisational problems. So I'm going to walk you through a very simplified version of the model. There's a lot more detail than this in the literature. But I want you to imagine that this is the environment of an organisation. Let's say you're talking about the council in Gothenburg that's tasked with developing climate change problems, and this is the environment that they're working in. Within that environment, they'll have various responsibility areas. So if you think of this as a university, these may be pools of students who are interested in different topics that you may want to pull into your university and give education to. You need operational units to deliver to the environment and to meet whatever needs there are in the environment. One of the key principles of the viable system model is that an organisation can only ever be viable if it's meeting some need in its environment. If it's a business organisation, that need might be quantified in money terms, but if it's a social policy organisation, that need is going to be in terms of the needs of the population or the needs of the ecosystems that they're dealing with. So the first issue that you have to deal with in organisations is saying what aspects of the environment is each operational unit going to be dealing with. And it's the operational units that do the front line work of the organisation. So if it was a university, those might be courses that are delivered to students. If it's a social work department, those might be different aspects. So there might be a mental health service, there might be a children's service, there might be disability services, etc. Now, if you've got multiple operational units in an organisation, you need some kind of coordination between those. So imagine, for example, and people who work in universities will know this scenario. Imagine you have a situation where you have one group who put on a new degree program and it's massively successful, and suddenly they've got 200 more students than they had previously. So they need more resources. This group down here is failing to attract students, and so they're contracting. One of the coordination questions is, can you move staff from here to here? Or if you can't move staff because of their specialisms, are you going to make staff redundant here but recruit here? There are these sorts of coordination questions that you always have to deal with. There are also questions of management, of the how you actually implement the strategy of the organisation on a day-to-day level, which involves auditing, understanding the work of these operational units. And one of the interesting principles in the viable system model, which I find myself repeating again and again to managers, is when you're actually managing an operational unit, that you don't want to get into micromanaging. You don't want the people who are the managers to be determining every day-to-day responsibility of what these operational units do, because they simply don't understand the variety of things that this operational unit has to do in relation to its environment. They have a much more attenuated understanding of what's going on. So what you do is you manage by setting upper and lower levels of acceptability. So if it's a university, again, people here who've worked in universities will know there's a lower limit below which if you recruit students, too few students, your course gets closed down because it's just not viable. There's also an upper limit where you can't fit the students in a lecture theatre anymore. So there's upper or lower limits of viability, and it's the responsibility of management to set those limits and really only interfere if the operational unit is about to transgress those units. Otherwise, they can be perfectly autonomous and get on with the job because they're the ones that can see all the detail going on in the environment. You also need foresight. You need to be able to anticipate changes in the environment that you're going to have to respond to. The function of foresight is also to look at the capabilities of the organisation and ask the question of whether it's going to be able to react to those changes, and if it isn't, to begin to ask questions about how things need to change. And you need strategy, or the overall identity maintenance of the organisation, which kind of sets the general direction within which all of these other things function. The reason these are numbered 1 to 5 rather, is because Stafford Beer was saying there's such an assumption in our organisations today that somehow the work of the board setting strategic direction is more important than the work of middle management, which is more important than the work of the shop floor workers. And he said that is a completely erroneous assumption, because if you take that view, then you're actually going to minimise the importance of the very thing that does the work. All of these things are equally important, and they're all necessary functions that have to exist in an organisation in order for it to be viable. You take any of them out and the thing will collapse. If there's no strategy, the thing can wander anywhere. If there's no foresight, you can get surprises that you weren't anticipating and be brought down by them. If there's no management, these things can start going off into any kind of direction. If there's no coordination, you'll find some people struggling to achieve their objectives, and you obviously need people doing the day-to-day work. The model also talks about the necessary communication pathways between all these different functions, which I haven't got time to go into. But it's a lovely little model, basically, that helps you, once you actually know the direction you want your organisation to go, it helps you actually look at how to keep it viable. Another principle that belongs with this model is recursion. So recursion means that it can exist at multiple levels. So what you should be able to do is open up this system 1 here, this operational unit, and within it you should be able to find all the same functions that exist in the whole within the part. So you should be able to find that it has its own foresight function, its own management, its own coordinations, its own strategy, although the strategy will be a strategy for that unit within the overall whole. So one of the things that I'm beginning to experiment with this now is how you can actually use this not just for single organisations, but how you can use it to coordinate across multiple agencies. So you can treat each agency as the system 1 here, and can you build a multi-agency coordination package using the rest of this. And one of my PhD students has just finished her fieldwork. She's been doing this in Chicago. Her name's Pam Sedelko, and she's been working with drug law enforcement agencies on the ground in Chicago and with international organised crime response, because what she's found is that the international organised crime gangs use local gangs on the ground for recruitment. So those gangs get involved in large amounts of violence to be able to prove themselves to the international organised gangs so they can get promotion, which means that you've got an international and a local level reinforcing each other, but none of the agencies are structured like that. They're structured either to deal with the local or to deal with the international. So she's brought these agencies together and looked at how you can create a multi-agency system. So here are some examples of organisations that have used this. It's been very widely used since the 1950s. Suma Foods is a whole foods cooperative in the UK. They made a really interesting decision. Through using the viable system model, they made a conscious decision that if they're going to maintain themselves as a cooperative and not become just your regular kind of big business, they actually had to limit their own size. And they defined their market niche in such a way that it would actually stop them from growing beyond the capacity that they wanted to be. And they're a successful business. Ministry for the Environment in Colombia, one of my colleagues, Angela Espinosa, did work with them, helping them restructure themselves. I did this work with one of my master's students. There was a community group in our local area, and it was responsible for providing services to unpaid community level volunteers. So it provided office space, meeting rooms, printing facilities, these sorts of things that anybody in the community could use. And it had grown and grown and grown until it had got to the stage where they realised that they were having problems actually managing the number of staff that they had now. And they asked us to help them restructure. So my student went in there and did the work, and he had everybody from the CEO down to the cleaners all in the workshop together, actually redesigning their organisation. And the upshot of it was really interesting. So the CEO who had founded this organisation came to the conclusion that part of the problem the organisation has is that she is interfering in every single level of that organisation. She put herself in every one of those systems from 1 to 5, and she said that's not appropriate for a larger organisation. She should be accounting for strategy and not interfering with the operational details. And she made the decision at the end of that workshop that she was the right person to have founded the organisation, but she's the wrong person to take it forward. And so she resigned, not in any negative sense, not that she felt pushed out. She saw the problem and chose to resign, and she went off and became a missionary in Vietnam, would you believe? Completely different career change. But the organisation basically restructured itself, and you can do it in a very participatory way. So as I was saying, it's possible to use the VSM for multi-agency coordination. I've done that 3 times now. Perhaps the most famous application, though, was to the whole economy of Chile under President Allende. So Stafford Beer was basically invited in by President Allende to look at how the whole country could be constructed. And there's a famous quotation from President Allende when they were doing this work with a viable system model, and they got to discuss System 5, which is the strategy and the identity of the whole, and he said, that's the people. So the idea was he built democracy into the whole process. The unfortunate thing is that if you go back to this model and you think about the anticipatory bit about how Chile needed to look at its environment and where the threats and opportunities were going to be, it didn't anticipate that the United States didn't want to see a viable model of socialism on their doorstep, and basically the United States removed President Allende. So although you can use a systems approach, it's not guaranteed to catch every eventuality. So would you like to take 10 minutes and have a think about the viable system model and how that might be useful in your climate change work? And I'll time 10 minutes. Okay, so let's kick off again. I'm going to talk with you now about some of the problems. We've talked about how we had system dynamics. Along with that, there were a bunch of other approaches like systems analysis, systems engineering. There's the viable system model. All of these are about talking about real-world systems and how you can model them to achieve some kinds of improvement, whether it's improvement in understanding the dynamics of large systems so that you can intervene, or whether it's improvement of an organization. And as you got into the 1970s, people began to expose some of the limitations of these ideas. And here are some of the problems that people started writing about. The first one I call the death of the supermodel, because especially in California, but in various other parts of the USA, people were doing some experiments. They were pouring millions of dollars into building models of whole cities or whole regions. And the idea was, if you could get the most comprehensive model possible, that you could answer any concern that policymakers might have. So the California experiments were the ones that I think really brought systems analysis at that time into disrepute, because they'd spent so much money on it, and they'd spent a lot of time in laboratories actually producing these models, and then they started talking to the policymakers, and the policymakers would ask questions, and they would say, oh, we haven't actually got that variable in our model, or we hadn't actually built a connection between those things, that'll take us another few months. And this happened over and over again until it became really patently obvious that building a supermodel to answer everybody's question actually ends up answering nobody's question. You actually have to model much more modestly for particular purposes, and then you can maybe answer some questions. It brought into question the whole limits of rational planning. There's a famous example in the UK where the government had commissioned some operational researchers to do some work on looking at where a third London airport should be. And they were looking at whether you should expand Heathrow or Gatwick or build Stansted. I can't remember what all the options were, but they came out with the optimal location for this new airport. And the politicians threw up their hands in horror and said, that's not optimal for us, that's in a marginal constituency and we'll lose the next election if we build the airport there. And people began to say, okay, well, maybe that notion of rational planning is problematic. You know, what's rational from one perspective maybe isn't rational from another perspective. And you have to think about different rationalities based on different perspectives. It's the limits of the social engineering metaphor this throws up, because there was, especially in that work with systems engineering and systems analysis around California, there was this belief that you could socially engineer whole communities, and you could treat people as if they're widgets in machines. But of course, people, when they know they're being treated like that, don't behave like that. So there's a limit to social engineering, and that whole term social engineering, which did used to be a positive in the 60s, has become a negative now. The limits of expertise, you know, you have a whole load of experts, whether they're stakeholders or whether they're researchers, working on solutions without necessarily engaging with the communities who are going to have to live with those solutions. And it threw up the limits of expertise. So some people deal with that by just refusing the term expert and saying we've just got to have participation. Other people say let's broaden the notion of expertise that include the expertise of the person who's actually going to be living with this. The limits of optimization as well. So there was a big move for using mathematical modelling to find optimal solutions. The problem with that is optimal from whose point of view? You can have the optimal logging of rainforests. That's not optimal from the point of view of somebody who's trying to preserve those rainforests. Any logging is going to be a problem. So it shows that there may be domains where you can get optimal solutions. So I think everybody would agree that we need ambulances and they need to be routed through cities using optimal routes. But plenty of other social policies can't be optimized in that way because these are about value judgments. Inability to deal adequately with multiple stakeholders and different perspectives, goals and preferences. Now that was the big one that really brought about the change. As people began to really think through what had to be done to take proper account of multiple stakeholders and different perspectives, that impelled a paradigm shift. And I'll talk about that in a moment. People also wrote about the self-justifying ideology of system science as comprehensive analysis. That's really interesting because you saw system scientists in the 1960s, when they saw that their modelling had failed and they were asked, well, what's the solution? A more comprehensive model, that's what we need. And that's a self-justifying ideology, basically. More of the same is always the answer. And that got severely critiqued, so something different is needed here. And objectivity can't be taken for granted. So the systems that are seen are the ones that are meaningful to the people participating. It's like the brain I mentioned earlier. So the brain is highly complex for a neurosurgeon, but it's a simple piece of meat for the butcher. So these are the kinds of problems people were throwing up. And a second wave of systems thinking was born. The 70s was a bit of a crisis time for systems, and really this came into its own again with a new wave of systems approaches from the early 1980s. So people started to model for particular purposes and explore those purposes rather than take them for granted. So they would actually begin to have discussions with different stakeholder groups and evolve the purposes through those discussions. It's the idea of multiple rationalities rather than an objective rational policy. So, I mean, what are the rationalities people are working with? From what point of view is this logical and what point of view is this not? Systems, the big shift from the systems point of view is that systems came to be seen as primarily conceptual. So a system is no longer just what's happening in the real world, but a system becomes my way of seeing the world that could be useful. So thinking system, that's when the term systems thinking really came into its own, because this is about thinking in terms of systems, and by actually exploring things in terms of systems as opposing to as assuming that the system really is like that, you get much more critical flexibility. And people get confused, and say, well, does that mean there are no systems in the real world? And in some ways that's the wrong question, because what this tells you is that you can see different possibilities for systems in the real world. And it's through thinking through those different possibilities that you get flexible thinking, get more responsive policy being developed. So people abandoned that social engineering idea in favour of engaging with self-conscious actors. The idea of democratising expertise came in via participatory practice. Now, I think there's no country on earth that's done more participatory work than Sweden, actually. It dwarfs what's been done in the UK. And optimisation approaches are still used, but they're really used for limited problems when there's a basic agreement on what the problem is and you can get an answer that everybody's willing to live with. importantly, taking account of conflicting values and viewpoints, policy preferences. So the notion of comprehensiveness gets turned on its head here, and you have the work of people like Wes Churchman and Werner Ulrich saying that systems thinking isn't about being comprehensive, it's about dealing with the inevitable lack of comprehensiveness. So thinking about your boundaries, thinking about what values are going to actually be influential in setting those boundaries, thinking about what the boundaries look like from different stakeholder perspectives. That actually helps you deal with the inevitable lack of comprehensiveness. So I'll give you one example approach here, strategic assumption surfacing and testing. So one of the big thinkers in this second wave was Wes Churchman, and he had two students, Mason and Mitroff, who were working in the late 1960s, and this is the approach that they developed. And what it does is it allows people who have conflicting views on what policy ought to be pursued to bring those stakeholders together in a structured dialogue to help them work through what ought to be done. And this is how it goes. So it's got four basic phases, the approach. You bring people together in groups. So let's say, let's make something up off the top of my head. Let's say you're dealing with a climate change issue. So you've got some people who want to put climate mitigation actions in. You've got other people who are still looking at the prevention of climate change and how you can actually have carbon neutral policies. You've got other groups who maybe are resisting this whole process and they want to see a business as usual scenario. And so you bring these people with different views on the policy situation together in separate groups. And working in their separate groups, they look at the various assumptions that their preferences are based on. So the ones who are actually wanting to combat climate change might talk about some of the assumptions that are built into climate models and these sorts of things. Some of those people who want business as usual might start talking about the assumption actually this isn't going to be as bad as people think, and that people are not going to accept the loss of their cars and these sorts of things. So they're assumptions that people are making. And then you bring people in to a dialectical debate, and that notion of dialectic, they kind of use the common view of dialectics, that you bring opposing poles together, and through the clash of those opposing poles something else will come out of that that will be more valuable than those parts going into it. But the interesting thing about that dialectical debate is that they're not simply justifying their propositions to each other. They're dealing specifically with their assumptions. And what they do is you take all those assumptions people are rating, and you get them to rate them on how important they think those assumptions are. So if my assumption is wrong, my whole proposition for policy falls over. So that if that's the case, it's high importance. If my assumption is wrong, the policy still stands pretty much. It's low importance. You also rate on certainty. So I'm really pretty certain this is right, and everybody else in the room will agree with this. And no, there's a lot of disagreement over whether this assumption is right, and we're really not sure. And you plot the different assumptions on this graph, and this will tell you where to focus the debate. So if you're talking about things that are both highly important and highly certain, those are the things everybody tends to agree with. You'll find that even though you've got lots of stakeholders taking different perspectives, they'll all agree on the things that are in this quadrant. You have things of high certainty and low importance. Those are the things you pretty much can set aside, because not only are they of low importance, but also you're pretty sure that that you know what they're about, so you can set those aside. The area where you want to focus debate is high importance and low certainty. Yep.
What if, so for example, in the States, we have a lot of people who claim that climate change is low certainty.
Yeah.
But in fact, it's high certainty. Like, how would that work?
Okay.
It's kind of
Okay, so but those people would put up those assumptions, and you'd start to debate them, and my way through that is that if you've got disagreement on this, it shows some element of uncertainty. So you would put it as high certainty. Sorry, so put it as low as low certainty. So you focus the debate on it. You want you know, you don't want to. If you've got a group that doesn't believe in climate change in the room, you don't want to not be debating climate change.
yeah.
So you need to be able to have that discussion. So you go for, you'll put the low certainty. This is the area because these are the really important things, but people are not sure about. These are the things that might need research. They might need people to actually engage on the assumptions. Yeah.
I was thinking about the debate. Do you have to agree in the debate, or can it just be a way of showing that it's a diversity between?
I'll get to that. I'll get to that.
I think that, but
Yes, I'll get to that. Basically, in the methodology as it was developed by Mason and Mitroff, yes, the idea was to converge. There have been a lot of people who talk about getting better mutual understanding can be the purpose, and you don't have to get an agreement. In fact, in some situations, it can actually be quite coercive to force an agreement. I think if you're developing a climate change policy, though, the necessity of having a policy means that you're going to have some kind of agreement. I don't know if this is the right approach to use in that situation. There are other ones I'll present later that might be better for that situation. But so this is the quadrant that you really focus debate on. But you don't want to forget this area. This is the area that often will bite people in the bum, because people think these things are not important, but the low certainty about them might mean those things will actually become important in future. So you keep those on people's radar. Now the idea is to move towards a synthesis perspective. What can happen is that sometimes one preferred strategy will win out over the other. Other times people will say, actually, we can have the best of both worlds here, and we can take this middle path, or there's a new emergent idea that happens through the process. What sometimes happens is that you cannot get agreement in that workshop, that the amount of knowledge in the room just isn't sufficient to resolve the areas of uncertainty. And you can then use that as a basis to create a research agenda. Do the research, whether that's research on work that's already existing in the literature, or whether it's new research, and then reconvene once that research is done. I actually think that's quite nice. I've never done it that way myself, but it's a nice way of actually getting people to agree on what gets researched in the first place, because that is such a problem. Usually you can't address value conflicts through science, because there's always one camp that will say you've researched the wrong problem. You can, through this, you can get disagreeing groups to actually agree the research agenda.
have you ever tried this?
I haven't tried that myself, but I can see it's possible to do it. I certainly have got stakeholders together to agree research agendas, but I've never used this for it. But I can see it's possible. So let's talk about a couple of examples. The most famous one was Mason and Mitroff's own project in 1969 with NASA. So NASA held a competition, a student competition, and they wanted innovative proposals that were going to be of relevance to NASA. And so Mason and Mitroff, in a challenging experiment, said we're going to set up a dialectical debate between those people who believe that NASA should be doing this space exploration, and those people who believe that it should be closed down and the money should be transferred to dealing with the problem of third world hunger. And so he brought these two camps into a dialogue. And frankly, the hunger camp won the debate hands down, and they came away saying that NASA should be closed down and the money should be used for something else. And the NASA rated these student experiments on innovativeness and relevance to NASA. They got 5 for innovation, 5 out of 5 for innovation, and they got 1 out of 5 for relevance for NASA. So this is the trouble of not having the decision maker in the room. So that report sat on a shelf. But interestingly, when Ronald Reagan was president, he reopened the question of what should happen with NASA. And they actually dug out that report again, and people were reading it. And you never can tell what happens to your research. Sometimes when you think it's been sidelined, it comes back again years later. That certainly happened with me when I did a project on feasibility study for an employment service for people with mental health problems. And there were government cuts, and the whole project was shelved, and I thought, nobody's ever going to act on this now. But 10 years later, they actually implemented the service. So somebody had kept it in their minds and did it when the opportunity arrived. So we did this in New Zealand. We did a massive project on water conservation and sewage services in this seaside town. We'd already done all the work on water, which was really quite difficult because there was a 25-year conflict between a council and its communities over conservation strategy. And we'd got through that work. They'd already realised that they could not carry on building more and more houses as they were, because there wasn't the water to support those houses. So they'd reached their sustainability limits. And the problem there was that they needed the extra rates, they needed the extra local government taxes from those new houses in order to fund the development of the sewage infrastructure, which was too old and it was failing, basically. So they were in a situation where they'd solved one problem around water conservation and put limits on, and now they had another problem because they couldn't fund the sewage upgrade. So we did this kind of process where we looked at all the assumptions that they were making around sewage policy, and having that kind of debate. And what was really interesting out of this, it's one of the very few times I've seen politicians absolutely putting their community's interests ahead of their own personal interests. Because what they realised is that this was unsolvable at the scale of community that they were working at, and that their only a way that they could get the investment that they needed for this sewage infrastructure was to surrender themselves as a political body, all collectively resign, and ask to become a ward in the jurisdiction of the big city that was in their neighbouring city. That's what they did. They all resigned. The city took them on as a ward. The big city funded the sewage infrastructure, and the guy who was the mayor of the small town was so popular for having sacrificed himself for the greater good of the community. Next election, he was elected as mayor of the city. So it was one of those nice little stories that kind of pans out. Would you like to do 10 minutes discussion of the relevance of this sort of approach for your problems, and then we'll take a break after that? Oh yeah, yeah.
How do you prevent these findings from not becoming too contextual? Because I'm imagining that, like, this 1969 project for NASA, that
Yeah.
it depends very much on where NASA is at currently,
Yes.
and what hunger is, like, what
Yeah.
the roots of hunger are
Yeah.
in 1969. And then if you were to pick it up in 1979,
Yeah.
then everything might have changed.
Different, exactly. This is about intervention, so it is about the context you're in now, and you've got to think about time boundaries. So if the future scenarios are important to the issue that you deal with, that has to be built into the project that you're doing. But this is always in context, always in context. You can't have absolutely generalizable knowledge on these things. And if you try to, often policymakers will say, well, this isn't relevant to my context. So, okay, would you like to take 10 minutes? And what we'll do is we'll take 10 minutes. I'll call out when 10 minutes is over, and then we'll take a 10-minute break after that, okay?